All right, I'll just say very quickly. Dr. Federica Raciti, she's a postdoc in the lab, and she's also a PhD. She's also a former PhD student, so she just kind of stayed in the Miami project. She never wanted to leave, and so that, yeah, the title of our talk should really be like, we're not spinal cord injury researchers, but please don't kick us out of Miami project. Um, but it's
Yeah.
about vestibular consequences of noise exposure. We just submitted a very large multi-PI grant that Federica is part of, and she really is helping lead a lot of this work. So,
Okay, well, thank you. Thank you for this introduction. So again, I'm Federica Raciti. I'm a postdoctoral researcher here in the Miami project in the lab of Dr. Rajguru. And today I'm going to talk about the effect of high intensity noise exposure in the inner ear. And particularly, I'm going to talk about the effects on the vestibular system. So noise is an ever-present part of our daily lives and is well documented that excessive noise can lead to hearing impairment. And currently according to the NIH, noise-induced hearing loss is one of the world's leading occupational diseases, with about 50 million adults in the US that show sign of noise-induced hearing loss and 30 million of subjects that seems to be exposed to daily hazardous noise. Both mechanisms and implication of noise-induced hearing loss are well studied. However, what's often overlooked is the potential effect of high intensity noise exposure to disrupt the delicate equilibrium, not only of the cochlea, but also on adjacent structures such as the vestibular system. So the vestibular system is a complex network of structures that is located within the inner ear, which plays a vital role in maintaining the balance and orientation of the body in space. And this is an intricate system that consists of 3 angular acceleration detectors, which are the semicircular canals, and 2 linear acceleration detectors, which are the utricle and the soccule, and of course the associated vestibular nerves, which provide real-time information to our brain about our body position and movement in relation to the gravity. So in doing so, basically, the vestibular system allows us to perform daily activities like walking, running, and adjust our body to maintain upright posture. So in addition to the vestibular system, there are other peripheral sensory systems that participates in controlling postural reflexes, mainly vision and proprioception. And so when peripheral vestibular loss occurs, the relative role of these other sensory systems increases, compensating for the limited of absent input of vestibular system. So, however, despite this compensatory phenomenon, the subject that present vestibular deficits have debilitating symptoms such as dizziness, imbalance, and vertigo that can significantly affect the quality of life. So because of the significant implication that dysfunction of the vestibular system entails for both workplace safety and the overall well-being of every individual, noise-induced vestibular loss has lately become a growing concern, with emerging research trying to shed light on the impact that loud, high-intensity noise exposure can have on the sensory system. So currently, most of the work that has been done trying to assess the features of noise-induced vestibular loss in human subjects has been performed on populations that are characterized by previous hearing issues or vestibular dysfunction or vestibular deficits. And so this makes kind of hard for the researcher to understand what is the real impact of noise exposure to the vestibular system. So for the past 2 years, here at the University of Miami, Dr. Snap, which is the chief of audiology, has worked in collaboration with the Fire Service Department to collect vestibular and auditory functional data in a clinically relevant healthy population known to be exposed consistently to high intensity repetitive noise, such as the firefighters. So interestingly, despite all the subjects were questioned are not concerned about issues in their balance or auditory function, they all show significant deficits in the auditory and vestibular function. So you can see here we have ABR response and CVEMP response, which represent measurements of auditory and vestibular function respectively. And we have the blue line, which are the age-matched control subjects, and the red line, which are the firefighters. And you can see that at any stage of their career, the firefighters present different and decreased responses, both auditory and vestibular.
Firefighters are also exposed to a lot of toxic.
Yeah.
chemicals, also a lot of areas of life person. I think that is coming up too. So there's some other variables here. Noise, I'm not going to say
Yeah.
noise is part of it. A lot of other, I think
Right. You have a.
No, he's absolutely correct. And I know that they actually have been trying to control as much as they could these variables. So for example, they have tried to implement protocols to clean their suits, I think, because one of the things that Dr. Guru and Dr. Snap were explaining is that kind of like having a dirtier suit means that it's kind of like a pride for firefighters. And so, but that carries also toxins that can affect vestibular function, but also can affect their central nervous system. So they have tried to implement protocols to like cyclically, like clean routinely their suit to kind of decrease that. So I think this is also, this is a way to kind of control a little bit more this population as much as you can control a human population.
And what's sort of like surprising is that less than 1 year of service, and these are very young firefighters, so these are typically 20-year-olds, right? They're just coming out of high school, straight going into fire service. And within that 1 year, we already started to see changes in the hearing and balance function. We started doing this clinical stuff. And that's what's really surprising.
there are high incidence of individuals in the military or to become firefighters.
Sometimes, yeah, but that's a little bit more of the mid-career for 10 to 19 years. They kind of like work in the military and then.
They're exposed in.
Yeah. So yeah, so what I was saying is that as you can see, like the waveform changes at every career stage as early as in the subject that have worked for less than a year. And this kind of suggests that the auditory function and vestibular function are mostly affected by the year of exposure to loud noise rather than age, just age. So most of the information that we have on the mechanisms underlying noise-induced vestibular loss comes from work in preclinical models. And so these preclinical studies have actually kind of determined what are the morphological and functional changes in the peripheral vestibular end organ following noise exposure, along with the potential effect that noise exposure can have on the central nervous system. And notably, these studies show a parallel between noise-induced damage of the vestibular system and hearing impairment. And though it is believed that the intense vibration that are caused by loud noises can disrupt the sensitive hair cell within the vestibular end organ, or even results in loss of vestibular synapse. And so the disruption of the sensory epithelium can alter the signal transduction process, potentially leading to the transmission of erroneous signal to the brain. However, despite this information are really valuable and important, there are significant challenges in translating these findings to clinical application. And one of the main obstacles lies in the assessment methods that is used in these studies, which do not offer a high translational promise as they cannot be readily applied to patient. So a direct comparison between preclinical model and real-world patient experience become challenging in this situation. So addressing this gap seems to be essential to kind of bridge the divide between our understanding of noise-induced vestibular damage in controlled experimental settings and its practical implication for individuals that are exposed to loud noise in their daily life. Oh, sorry. So the limitation in translatability emphasize the need to further research and develop some techniques or assessment that can be used both on human subjects and clinical model. As such effort can provide valuable insight into the prevention and treatment of noise-induced vestibular loss in a clinical context. So in the last 2 decades, vestibular evoked myogenic potential have emerged as a critical tool to that allows ear-specific evaluation of the otolytic function. These are short alteration of myogenic activity that are evoked in response to different stimuli. We have air-conducted stimuli, bone-conducted vibration, or galvanic pulses. And because of the features of the stimulation inputs, as well as the physiological output that are measured, this assessment, unlike others that are used in clinics, seems to have the most translational promise. So due to the diverse neural projection of the branches of the vestibular nerve to different muscles, VAMP can reflect the activity of either the saccular or the utricular end organs, depending on the placement of the recording electrode. So the first VAMP assessment is called cervical VAMP, and the cervical VAMPs are mediated by ipsilateral reflex pathway that originates in the saccule and then projects to the motor neurons in the sternocleidomastoid muscle via the inferior vestibular nerve, the vestibular nuclei, and descends the vestibulospinal tract. And it reduces the tone of the sternocleidomastoid muscle. So then the other assessment that we have is the OVAMP. OVAMP, or ocular VAMP, is mediated by contralateral reflex pathway that originates in the utricle, so not the saccule but the utricle, and projects to the motor neuron in the inferior oblique muscle via the superior vestibular nerve, the vestibular nuclei, and then the longitudinal fasciculus and the oculomotor nucleus. So overall, given the utility of VAMPs in the clinical domain, it seems to be necessary to examine the neural basis of the response and validate the relevant features in preclinical model. However, the works that are currently present in the literature have focused only on determining the neural pathways of the response to air conducting stimuli, while little is known on the effect of the stimulus, the effect of the stimulus parameters to the actual myogenic responses. So for the past 2 years, for this reason, for the past 2 years, in our lab, we have worked trying to develop a repeatable and reliable CVAMP setup and protocol to ultimately provide novel information on the tuning of autolytic afferents for frequency and intensity of air-conducted stimuli in a rodent model. So here you can see, I don't know where. Okay, so here you can see an example of the setup that we have developed. So we have a custom rat holder that presents also a head holder, and the head holder helps tilting the head of the rat so that we can maintain the tension in the sternocleidomastoid muscle. Then we have where we then place the recording electrode, and the electrode has to be placed perpendicularly to the muscle. We then have a reference electrode in the vertex, a ground electrode in the hind limb, and the acoustic stimulus is delivered via an in-ear speaker in the same side where the recording electrode is placed. So this is an example of the type of vestibular responses that we're able to evoke. So with this study, as I said, we wanted to kind of understand the tuning of the autolytic afferents to sound. And so we have tested a broad range of intensity and frequency and recorded the vestibular responses. And interestingly, of course, the parameters, the metrics that we have analyzed of the vestibular responses are threshold, amplitude, and latency. So interestingly, what we have observed is that while threshold does not seem to be affected by the frequency of the stimulation used to evoke myogenic potential, both amplitude and latency of the responses at any of the intensity that we tested seems to be affected by the frequency used. And in particular, we have observed that frequency between 6 to 10 kilohertz seems to evoke larger and faster myogenic potential compared to lower frequencies or higher frequencies. So this information is actually really important and interesting because the few papers that have tried to, where people have tried to evoke cervical myogenic potential in preclinical model use only 1 kilohertz as input stimulus. And this is because 1 kilohertz is the frequency that is mostly used in the clinics to test vestibular myogenic potential in patients. So using our novel setup and the knowledge that we have gained from our study and our characterization in control subject, in the past year or so, I have worked on trying to characterize the features of noise-induced vestibular loss in basically all the models that I had currently available in our lab, with the ultimate goal to kind of determine which are the possible differences and similarities between the functional output that might provide valuable information to better understand the mechanisms underlying noise-induced vestibular loss. So as you might know, part of our lab focuses on the study of noise-induced hearing loss. So really, I had access to a lot of models of animals that have been exposed to different type of trauma. So these are the 4 cohorts that I have tested and that I'm going to show the results today. So we have cohort A and cohort B, which are animals that have been exposed to broadband noise. So noise between 4 to 16 kilohertz at 100 decibel SPL for 1 hour. The difference between cohort A and cohort B is the age of the animals. So cohort A consists in animals young animals, so between 14 to 18 weeks. And then we have cohort B, that consists in animals that have an age between 54 to I think 57 or 58 weeks. We have then cohort C. In cohort C, we exposed our animals in younger population to narrowband noise, so noise that has a bandwidth of between 4 to 8 kilohertz. And then we also tested cohort D. Cohort D is a cohort of animals of young age, so 14 weeks, that have been exposed to blast between 12 to 19 PSI. In all the cohort that we have studied, we performed functional assessment of their hearing and vestibular. So for hearing, we use ABR. To test vestibular function, we use CVAMP. And then we also perform confocal imaging of the vestibular structure, trying to understand or see if there were evidence of anatomical and morphological changes after noise or blast exposure. So now I'm going to show the functional results that we have obtained for all the cohorts that I have just mentioned. So this is an example of this experimental design that we have used for this first cohort. This first cohort is cohort A, so younger subject that have been exposed to broadband noise. We performed functional assessment of auditory and vestibular function before noise exposure. We then exposed the animal to noise, again, 4 to 16 kilohertz at 100 decibel SPL for 1 hour. And then we tested vestibular function at different time points from day 1 up until day 28. At day 28, we euthanized the animal, collected the vestibular sample for further testing. So because of the information that we have gathered from our characterization study in control subject, we looked at CVAMP responses that were evoked by 2 different simulation frequency. We have 1 kilohertz, because again, is the frequency that is mostly used in all the papers that we have found so far, and 8 kilohertz, because as I mentioned, 8 kilohertz seems to be one of the frequencies that give us the largest CVAMP response and faster response as well. The metrics that we look also in this case are threshold, amplitude, and latency. So I'm going to start with the first parameter that I'm going to talk about is threshold. So this metric is commonly used to assess functional changes in electrophysiology. And so it makes an important feature for the characterization of the VAMP responses in our trauma models. So as you can see here, after noise exposure, we observe a significant shift in the threshold that occurs at day 1. This shift is, however, temporary, and we show full recovery by day 14 and day 28. When looking at the amplitude of CVAMP responses that have been evoked by 1 kilohertz stimuli at a suprathreshold level of 90 decibel SPL, we observe after noise exposure a significant decrease of the amplitude of these responses that is permanent. So over time, it seemed like we have some partial recovery, but the overall amplitude of these CVAMP responses seems to be decreased compared to the amplitude that we have obtained before exposing our animal to noise. The last parameter that we're going to look at is the latency. Again, latency of the CVAMP responses evoked by 1 kilohertz stimuli at 90 decibel SPL. As you can see here, after noise exposure, we have a significant increase in the latency of the responses. However, compared to what we've shown for amplitude and threshold, this increase is kind of like a little bit delayed in our time points. So the peak latency that we reach occurs at day 7. The shift in the latency of our animals after noise exposure, however, is temporary, and we observe full recovery by day 28. here are the results from the CVAMP responses to 8 kilohertz stimuli. Again, we observe a significant increase in the threshold after noise exposure that reaches a peak at day 1. And again, this threshold shift seems to be temporary with full recovery by day 28. We observe again a permanent shift towards a lower amplitude of these responses to high frequency stimuli. And we observe regarding a latency, an increase in the latency, again, that seems to be a little bit delayed compared to what we observed for threshold and amplitude. But in contrast to the responses to lower frequency stimuli, this type of shift seems to be permanent. So again, at day 28, we have a permanent increase of the latency. Okay, so then we looked at the second cohort, so cohort B. The difference is, so we have performed the same type of noise exposure. So we again have 4 to 16 kilohertz and 110 decibel SPL. Again, the difference between this cohort and the previous one is that this cohort consists of older animals. And the reason why we wanted to test older animals was to kind of understand if age might actually have an impact on how noise can affect vestibular function. The experimental design is exactly, yes. Sorry? Well, yes, but these are short-term studies, so we actually euthanize the animal at day 28. So we have like the 14 weeks animal have been kept for a month and then have been euthanized. Technically, we could do a long-term study and keep an animal and test it at longer time points.
Sorry, previous slide was.
Yes. Yes, but the animals have been exposed to noise were 14 weeks old. In the second cohort, we exposed our animals to the same noise protocol, but the animals were 54 weeks old. So it's our 2 different cohorts. The delay in assessing?
Here you start assessing day 1.
Yes. And also in the second cohort, we started assessing at day 1. It's just the age of the animal is different. Well, we kind of wanted to know in a short term, since no one has done this before, we wanted to know if there were also associated like anatomical and morphological changes after noise exposure in our short-term study. So we just had our animals at 14 weeks, we exposed to noise, we measured the we did functional assessment up until day 28, and then we euthanized the animal because we wanted to collect a sample. We are currently working on longer term experiments. So we have exposed our animal at a young age and we're keeping the animal for like 1 year to assess if aging.
Here's the age and the variable in the second experiment. Why we did the second experiment.
Sorry, can you?
Young animals would be assessing hearing.
And vestibular function, yeah.
And second, age.
No, I'm doing like the same vestibular and hearing assessment in just in aged animals, just to see if animals that are older. Yes. Yeah, they are two parallel. So exactly. So are exactly the same. No. They are. So I'm showing only. Yeah. What happens? Yeah. So we just wanted to see. Yeah, we just wanted to see if age could actually have an impact on how noise could affect vestibular function. So we did in the younger cohort, we did the functional measurement of vestibular function, and then in the older cohort, we did the same exact experiments. We did vestibular and hearing assessment. So
I don't think age has anything to do with your ability to hear.
The way you can think about it is this is to assess when you go to a concert.
Yeah.
And when I, at my 21-year age, go to a concert, how are our ears gonna be affected differently?
I don't understand this.
Okay.
Okay. So, so here there are the results that we have obtained from this cohort. So what we see is that after noise exposure in the older cohort, we observe an increase in the threshold, so a significant threshold shift that seems to be permanent over the time frame that we considered, so the 28 days. When looking at the amplitude, we have a significant decrease in the amplitude that again seems to be permanent over time. However, in contrast to what we have observed in the younger cohort, it seems that noise exposure does not affect the latency of the CVAMP responses in this age cohort. We looked again at the same metrics and the same metrics for the CVAMP responses to 8 kilohertz stimuli. And when looking at the threshold, again, what we see is a significant increase in the threshold after noise exposure. However, in contrast to the responses that are obtained by 1 kilohertz stimuli, the thresholds seem to recover by day 14 and day 28. We also observe a temporary shift in the amplitude of the responses after noise exposure in this cohort. And again, similar to the results that we have obtained from the 1 kilohertz cohort, we show no difference in latency after noise exposure. Yes.
Trying to understand the y-axis. So what you're measuring here is the shift, which means the difference from the baseline.
Yes.
Right. So no changes in latency doesn't mean that there's no latency. So could this be misleading that the older animals already have latency?
Okay, so I'm showing only shifts because I think they might be a little bit easier to understand, but I also have performed all testing comparing the raw data. And we show that between older animals and younger animals, there's no difference in the latency, amplitude, and threshold of the CVAMP response at any of the frequency that we test. So that's why I'm showing this. And but yeah, like if you want to see the data, I can show you. Huh? Between 54 to 58 weeks. Yes.
The setup is exactly the same with younger and
it is the same. The next slide. Yeah, so at this point, we wanted to compare what happened between younger and older cohort. And as you can see here, we have regarding the threshold, we show basically like we show a very similar pattern. So after noise exposure, we have an increase in the threshold that seems to recover over time. A similar pattern for the amplitude. And however, the latency, while it seems to be highly affected in the younger population, this did not seem to be affected in the older population. And again, this is a comparison of the CVAMP responses between the two cohorts in the 8 kilohertz stimuli. We have again threshold, similar patterns. We show that the amplitude decrease in the younger population is more prominent than the amplitude decrease in the older population. And again, we show that there is a significant difference between the shift in latency observed in the younger population versus versus what happens in the older population. So, okay, overall, these results kind of suggest that the age of what the animals have been exposed to noise can actually impact their vestibular function. So then we have a third cohort. Our third cohort, or cohort C, is the cohort of younger animals, 14 to 18 weeks old, that have been exposed to noise, narrowband noise, so 4 to 8 kilohertz at 100 decibel SPL for 1 hour. Again, we used the same experimental design. So we recorded after noise exposure, we did functional assessment of their hearing and balance function at day 1, from day 1 to day 28. Day 28, we euthanized the animal, collected the sample for future experiments. Again, we look at CVAMP responses to 1 kilohertz and 8 kilohertz stimuli, and we look at the same metric, threshold, amplitude, and latency. So here are the results of the CVAMP responses to 1 kilohertz stimuli. What we observe here is a significant shift in their amplitude after noise exposure that occurs as early as day 1. It seems to be permanent up until day 28. A temporary shift in their amplitude of the CVAMP responses to 90 decibel to 1 kilohertz stimuli at a super threshold level of 90 decibel SPL that recovers by, I think this is day 14. And similar to what we have shown for the older cohort, we observe no difference in the latency of the CVAMP response after noise exposure, after narrowband noise exposure. When looking at the parameters for the CVAMP responses to 8 kilohertz stimuli, again, we observe a temporary shift in the threshold of the CVAMP response that occurs at day 1 and recovers as early as day 3. And we observe no significant difference in the amplitude and the latency of the response to 8 kilohertz stimuli. So finally, we have our final group, which is the blast exposed group. Here, the experimental design is a little bit different. So again, we have a pre-trauma measurement of the vestibular and auditory function. We have blast exposure, and then we have functional assessment from day 7 to day 28. As you might have noticed, we have not performed functional assessment before day 7. And this is because what we observe is that after blast exposure, there is a perforation of the tympanic membrane. And so perforation of the tympanic membrane could actually cause a change in the conductance of the overall inner ear, making the functional data collected unreliable. So what we did was to check the status of the tympanic membrane over several days, and then we started our functional assessment when the tympanic membrane healed completely. And what we saw is that in all our animals, so this is probably 19 animals, the tympanic membrane healed completely by day 7. And so this is why our first functional assessment occurs at day 7. So again, we looked at the CVAMP responses to 1 kilohertz stimuli. So at low frequency stimuli, what we saw is that after blast exposure, we have a significant shift in the threshold of these responses that is permanent over the time frame that we looked at. We also observe a temporary decrease in the amplitude of the CVAMP response that recovers by day 14, and we observed no significant difference in the latency of the response after blast exposure. When looking at the response at high frequency stimulation, such at 8 kilohertz, we observe a temporary shift in the threshold that occurs at day 7 with full recovery by day 14. However, this is accompanied by significant decrease in the amplitude that is permanent over the time points that we looked at. And again, similarly to what we have shown for the responses to low frequency stimulation, we observed no changes in the latency of the response.
Can I ask if you, because morphologically or structurally, it looks like the tympanic membrane is going back to intact. Don't experiment to see if it's functional.
So no, but this is something that we're going to do in the future. Actually, we are, I think we are buying like an otoscope. Yes. Yes. So we can also assess if there's difference. Yeah. Yeah. Yes. So.
Yeah, great question. Thank you.
Male, sorry. Yeah, sorry. I didn't. Yeah, no, I cannot. I worked in a noise lab for too long, so. Yeah, all male, sorry. Yes.
The first exposure is where decibels and hertz and 20 PSI, how do they relate to in terms of volume of exposure? What is the blast of the broadband? 10 times concentrated?
Yeah, but the blasts happen within like.
Yeah.
Whereas
So.
the noise exposure is 1 hour long, so there's very different characteristics. But when you look at the area under the curve, like, they come out. Okay. For this is similar.
It is,
But it
yeah.
involves very quick.
Yeah. So, yes.
In terms of the male-female differences, since you're only testing males, men have a tendency to lose the hair cells that operate under a woman's frequency in terms of than the other one. So do you see any type of that difference in your rats?
I have tested only males, so we'll see when I test females if they are more responsive.
Very different literature on
Yes. Yeah.
In fact, like, people are trying to use that as a treatment, for sort of like reducing hearing loss.
Yeah.
But within the age group that we have,
Uh-huh.
we typically don't see sex indicators. For both the biological sexes, we see that the value is the same. It's when you start getting into beyond 60, 70 weeks is when you start seeing.
So I can blame my hearing loss on the fact that I'm post-menopause. I have no estrogen.
Yeah,
Ingestion in my body.
Yeah.
That's why I don't hear it.
not to all the parties, yeah.
So the leading hypothesis in the field regarding the primary cause of noise-induced vestibular loss revolves around the notion that this intense vibration that is generated by loud noises can disrupt the sensory epithelium of the vestibular end organ, and this results in alteration of their normal function. So among these end organs, the saccule is considered the most susceptible to such injury because of its proximity to the stapes foot plate, which is most likely the point of injury in cases of high intensity noise exposure. So numerous studies that are conducted in preclinical models have provided compelling evidence supporting these hypotheses, and they have demonstrated that exposure to high intensity noise can lead to a range of anatomical and morphological changes in the periphery of the vestibular system. So these changes may include hair cell loss. So high intensity noise can cause loss of hair cell over a period of time. And this is the hair cells are essential, of course, for detecting motion and spatial orientation. They also observe saccular collapse. So the saccule in particular has been observed to be vulnerable to structural damage, including collapse. And this happens in particular to exposure to noise at high intensity or blast exposure. Macular disruption, so the disruption of the macula of both otoliths, so utricle and saccule, and also noise exposure seems to lead also to hair cell atrophy, potentially impairing the function of the hair cell and their ability to transduce signals. So importantly, the effect of high intensity noise exposure seems to be dose dependent. And so the intensity of the vibrational forces may impact different regions of the sensory epithelium to varying degrees. And so the dose dependence response could actually somewhat explain the variety of outcomes that we have observed from our different cohorts. So as I mentioned before, in our short-term studies, we have euthanized the animal at 28 days because then we wanted to look at the morphological changes of the saccular macula. So usually when we look at morphological changes, we look at hair cell number and changes in the directionality of the hair cell bundle of the hair cell. And this is a task that is done manually. So you collect you have a confocal imaging, you sit down and literally count all the hair cell. So this is a very time-consuming task. Sometimes can be tedious. So to kind of move forward and make this process a little bit seamless, we have developed a MATLAB code where we could input our confocal images, and this code, using a series of area filter or intensity filter, could actually detect the hair cell, the hair cell, and provide a number and provide information on the directionality, ultimately providing an accurate morphological map of the vestibular, of the sensory epithelium of the vestibular end organ in a short amount of time. So we have preliminary data only from 2 groups of the 4 that I have shown you today. We have all the samples, but this is a very long process. So we have preliminary imaging data from the younger cohort that has been exposed to broadband noise, and the cohort that has been exposed to blast. So we look at the hair cell number specifically for the saccular macula of the younger cohort that has been exposed to broadband noise. And what we see is at 28 days after noise exposure, we observe no difference in the hair cell number of the animals that have been exposed to noise compared to an age-matched control. In contrast, when looking at the hair cell number in the saccular macula of the animals that have been exposed to blast, this seems to show a reduced number of hair cell compared to their age-matched control. So overall, in our short-term study, after this injury, the functional and morphological feature of the vestibular system of the trauma model differs significantly. And this might suggest that there are different mechanisms underlying noise-induced vestibular loss that occur in these different models. Yes.
So, not a field, so you're gonna correct me, but the cells you're analyzing here, I guess, are temporally differentiated cells, okay? So, did you also think about checking the stem or stem or progenitor cells remaining in the population? Because I guess this is the repairment, right? So, it would be interesting if in parallel to temporally differentiated cells that repair the tissue, you got alterations in the number of stem or progenitor cells. Now, this is when I'm out of the field.
Yes. So I think people look at also supporting cells, because supporting cells in the vestibular epithelium and in the cochlear epithelium are known to have kind of like, it's not that they cannot, like they have a potential to generate hair cell, to become hair cell. But this is a very, I don't know, this is a very complicated topic. And it's like, it's really like, usually people don't look at progenitors or other hair cell type when they look at vestibular or cochlear damage. They mostly look at hair cell loss. And this is what we started. And because this is a very like new field, we haven't found anything. So we just started with what we know.
Hair cells really don't degenerate.
Yeah, they know.
Supporting cells.
Yeah, the supporting cells are, yeah, exactly. So they have the potential, but
because hair cell loss is terminal, we kind of use that as a first point.
Yeah, but that's for sure. That's
Yeah.
a way to measure
Yeah, yeah.
damage specifically, and I see that. I'm thinking about a person that gets exposed to several blasts. What does he get back the cells that should be better?
yes.
Is he losing, the potential in time?
Absolutely.
Yep.
No, I think that's a great question.
Why did the cell die? What's the molecular mechanism for the cell death?
For the cell death, I think there are a few mechanisms. I know that there's a mechanism of apoptosis that is triggered by noise exposure in the cochlea. There's also, I think, from the study that Raquel has done, another cell death pathway that is activated by noise exposure is pyroptosis too.
You're on the great.
Laboratory, cells in that field?
So I haven't looked, and I know that not many people have looked at, because so collecting vestibular tissues from fresh samples is very, very hard. So all the samples actually come from like fixed animals. It is a very, very fragile tissue. So dissecting a fresh utricle or a fresh saccule or a fresh semicircular canal is really hard. And I know that ideally this would be the perfect sample to do, I don't know, RNA-seq, or we can do also like a FACS analysis to kind of understand which type of hair cell, which type of cells are present in that tissue after trauma exposure. But so far, I don't have the equipment and to do that. Yeah. 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 Yeah, this is something that, yes. So, yes, so this is it. So this, with this work, we have tried to detail the profile of sound evoked myogenic potential in different trauma model of vestibular noise-induced vestibular loss. And this information can lay the foundation for characterization and study of the pathophysiology, and with the purpose of developing novel therapeutics that can be used to treat vestibular dysfunction. And with that, I would like to thank my mentors, Dr. Rajguru and Dr. Snap, all the people in the lab that helped me throughout this whole process, as well as the funding agency. Thank you.
That's like a lot of rock concert when they're young, and then as they grow older, maybe expose them to another secondary stress. And see if that.
Yes.
What? See if it affected their hearing or.
Yeah.
Their function or something like that, right?
Yeah.
So that's like, Dr. Kerr is collaborating on that project, Dr. Kerr. Nadine Kerr, is collaborating on that project. So the idea is to essentially look at that. If you have, because clearly what you see from the first data set that she showed is that younger animals seem to react differently to the noise exposure. And it's much more severe than in the older population. Now, there is a type of hair cell that is lost as we age. Yes.
Yes.
Continuously. And so the difference might be that all of the structures that you are losing along with that hair cells are what are more affected in the younger population. What we don't know is what is their role in terms of eventual equilibrium and balance, right? We know that they play a big role in fast acceleration. So when you get up from the chair, those are the cells that are going to get activated and detect. So as you age, does this hidden sort of vestibular loss become even more significant in terms of cognitive load that you need to function, right, in your daily activities? So that's where, like, I think the studies with Dr. Kerr and all these different groups that Federica has already started will give us a lot of information. And none of this data exists, so.
Thank you.
Could you actually measure equilibrium in these mice after?
So this is something that we're working on. We are trying to develop a new setup to determine and measure the gait of the animals after noise exposure. So, and we are like tracking, we also are working with Yuan, I think, on developing like an algorithm to track the animals along a platform so that we can provide also behavioral assessments. Because what we have right now in the field is just a measurement, like a time measurement. So how long it takes for the animal after exposure to a specific trauma to complete the task, that is walking from point A to point B. But we know that when we look at balance, we also want to walk it this way at the gate and everything. So we're trying to implement these techniques to get this data as well.
Thank you.
Is this an event that you have weekly?
I wish, honestly. He is. We usually ask him to take the selfie because no one else wants to have a big face in the picture. So
Great.
thank you.